thank you, Langston, and thank all of you for inviting me here. And it's a pleasure to be able to tell you a little bit about stuff that I do and the whole quantum world. So I'm not going to really assume that you're that familiar with quantum computing, but if you are and you want to speed me up, or if you want to slow me down, feel free to interrupt and do either of those things. I'm not used to being mic'd up, so my voice seems to be like everywhere at the moment. And can everyone hear me okay? Okay. So I'd like to start by giving kind of a brief introduction to quantum information. So let me call this quantum basics. So it helps to contrast classical computing with quantum computing. So a bit is an element of 0, 1. A quantum bit, or qubit, is a unit vector in C2. So it's a pair of complex numbers, and usually we take, as a basis of this space, we take something called ket 0 and ket 1. So we can picture this space as a two-dimensional space where ket 0 is along the x-axis and ket 1 is along the y-axis.
So just to be clear, this is regarded as a vector space where the scalars are complex numbers?
That's right. So a typical state in this typical qubit will be called ket psi. You just read that as psi, which is alpha times 0 plus beta times 1, where alpha and beta are complex numbers. And it's supposed to be a unit vector, so that means the norm squared of the coefficients adds up to 1. Okay, so examples of qubits, well, ket 0 and ket 1. Oops. There's a state called plus, which is, if I draw a unit circle here, it's what you get if you go out a 45-degree angle. So that's the state plus. And that's 1 over root 2 times ket 0 plus ket 1. And this is called the equal superposition of 0 and 1. There's also a state called ket minus, which is 1 over root 2, 0 minus 1. So that's the unit vector that points in this direction, I guess. Minus is down there.
Intuitions about what these represent?
Sorry?
Are there some intuitions about what these various qubits that you're seeing represent?
Well, I guess you can think of this as polarized light, for example. If you're thinking about a physical system, there are many physical, the physicists tell me, and I'm not a physicist, but the physicists tell me that there are many ways to create qubits by physical systems such as polarized light or by...
I'm just kind of, I don't know much about it. 0 and 1?
Yeah.
0 is kind of something is not the case, 1 is the case. Is there some kind of situation generalized here, or are we going to go completely abstract and just in vectors here?
I guess I'm going to give you, my plan was to give you a mathematical framework for how quantum information is stored and processed. And the people that study our actual universe tell us that this is actually how our universe works. That the state of our universe is a unit vector, can be thought of as a unit vector in a very high dimensional space, and so let's maybe just leave it as a mathematical abstraction that way. But I think it'll become clear maybe if you have a physics background, you're probably already thinking about spin up and spin down and that kind of thing. Okay, so so that's a qubit. What if you have many bits? Many bits, of course, is just a string, 0, 1 to the n. Multiple qubits, an n qubit system. N qubit system. Okay, so there, instead of taking 0 and 1 as a basis, we're going to take all n-long bit strings as a basis. So that's a unit vector in C2 tensored with itself n times. So for example, a 2-qubit system will be a linear combination of the 4 basis elements 0, 0, 0, 1, 1, 0, and 1, 1. And these will have coefficients, alpha, beta, gamma, and delta. And we're going to require that that's a unit vector. So the square norms of those complex numbers add up to 1. So one thing that is sort of apparent immediately is that this is, from the point of view of classical computing, this is an enormous amount of information. N qubits would be representable by 2 to the n complex numbers. And even if you only use finite precision for those complex numbers, that's kind of an enormous thing to keep track of. But the idea is that nature is automatically keeping track of that for you. That's kind of maybe the trick. The trick to quantum computing is that we're tricking nature into like doing computations for us because this is the way our universe apparently works, or so I'm told. Yeah.
Just a question, and it could be because maybe I didn't understand that representation, but
yeah.
So you gave some examples of where the qubits can be in this plane.
Yeah.
Is it discretized? Like, are there specific positions that it has to go to, or like on that circle, on the unit circle, can it be anywhere? Like, is it say?
Theoretically, it can be anywhere. Yeah. In practice, probably whatever physical system is implementing this, you're going to be doing operations on this that only take it to a finite number of states.
But in the math we're looking at, in that representation, as long as it's a unit, it can be anywhere in that complex.
That's right.
Plane.
Mm-hmm. That's the way we're thinking of it. Yeah. Okay. So this is the way that quantum information is represented. How is information processed? So I'm thinking about over here. You would think about logic gates or whatever model of computation you have that processes classical information. The analog over here is linear transformations. So the analog of I'm just going to kind of erase down here and say the analog of logic gate is linear transformations, specifically unitary transformations. So those are linear transformations that preserve the length of a vector. So if you apply a unitary transformation to a quantum state, you will again have a quantum state. So examples. There's a function that looks like 2 by 2 matrix that looks like this. That takes the 0 state to the 1 state. So we're imagining that this basis is ordered so that the 0 and the 1 represent the first and second columns. So this is the thing that interchanges a 0 and a 1. So that's like a knot. That's called X in quantum speak. You could also do there's something called H, which is 1 over root 2 times 1, 1, 1 minus 1. This is called a Hadamard transform. What does it do to 0? It takes 0 to the plus state, and it takes 1 to the minus state. So H of 0 is equal to plus, and H of 1 is equal to minus. Okay. So effectively, it's a rotation, a 45-degree rotation of the plane. Yeah.
Is it accurate to think that all of these unitary transformations are rotations of the unit sphere?
Yes. So any unitary, you can think of you can think of a unitary transformation as a rotation, or reflections are also unitary.
So is h squared equal to x then?
Sorry?
Is h squared, or h equals with itself, equal to x?
Well, let's see. So if you're going to do h of 0 and get plus, if you do h of plus, then you're back to 0, turns out. So you put a 1, 1 here, and you multiply, you get 1, 0. Yeah.
It's self-inverse.
Yeah, that's right. H squared. That's an important property of H, is that H squared is the identity. Yeah, that's right. Okay. Other questions?
Just the very basis here. So we said a qubit is a unit vector in C2. So that means that it's 2 complex numbers.
Yes, it's alpha, and we're kind of 0, 1 is a basis here, so we're thinking of this as alpha, comma, beta. If you wanted to write this as a column vector, you would write it as alpha, comma, beta.
I'm not sure what we're drawing, because that is only 1 dimensional.
Oh, so I'm thinking of this axis, even though this axis looks like it's a real dimension, I'm thinking of this as a complex dimension. Yeah. Of course, it's impossible. I mean, it's beyond my talent to draw a 4-dimensional picture. So we represent C2 basically as R2. Yeah.
But then the kind of some of the intuitions for 2-dimensional space apply to that when the axes are complex, like rotations.
Yeah, I think it's fair to say that some of the intuitions apply. Some of them don't. There's something called the block sphere, which is kind of a more accurate representation of what a single qubit is. But for our purposes, I mean, we've already used the intuition here to think that H is this sort of rotation.
The usual rotation by 45 degrees doesn't cancel itself out. Right?
Well, I guess it's more like it's probably more like a reflection then, because I think this intuition should be right, because 0 goes to plus and 1 goes to minus. Yeah, so it's sort of a reflection.
Oh, okay.
Yeah.
So x is also a reflection, sort of around the different axes.
Yeah, X is a reflection around plus. That's right. Yeah, right. Exactly. Great. All right. So these are good questions. I hope we're sort of getting the hang of this. Okay. So that's representation, processing, and then there's output of information. So classically, that's sort of trivial. Your memory says exactly what you think it's going to say, and you look at it and you see what's there. In quantum mechanics, you can't do that. So we know that whenever we observe something, it forces it to collapse. And so here's the mathematical model for that. It's called making a measurement. I kind of want to leave some of this, so I'll just kind of scribble up here. So I'm going to tell you what it means to measure in this basis. So if you measure psi, what happens is psi collapses either to the 0 state or to the 1 state with probabilities equaling the square norm of the coefficients. So with probability norm alpha squared. And this is with probability norm beta squared. And because of this identity, one of those things will happen. Okay. So measure is a process. If you have if somebody hands you a qubit, you can choose, if you wish, to measure that qubit, and the output after you measure that qubit will either be a ket 0 or a ket 1, and this will happen with probability alpha squared, and this will happen with probability beta squared. And after that, the qubit is destroyed. It's collapsed into either the 0 state or the 1 state. You can't do it again. That's right, yeah. Okay, so for example, if somebody handed you a 0 state and you measured it, you'd always see 0. If somebody handed you a plus state and you measured it, then half the time you would see a 0 and half the time you would see a 1. If somebody handed you a minus state, similarly, half the time you would see a 0 and half the time you would see a 1. Okay. Suppose somebody, so go ahead. Okay, that's exactly. So I've got a state in my pocket here. I'm guaranteeing you that it's either a plus or a minus. Tell me which. Well, what you certainly don't want to do is measure it, because if you measure it, it's going to be sort of indistinguishable from that point of view. So what are you going to do? You're going to take the state that I hand you. You're going to perform a Hadamard transform on it. Hadamard will take, if I handed you a plus, it will take it to 0. If I handed you a minus, it will take it to 1. After you've performed the Hadamard, then you can measure the state and determine with probability 1 whether the original state was a plus or a minus. Does that make sense? So even though on the surface it appears maybe that plus and minus are somehow indistinguishable, in fact, they're perfectly distinguishable. And in fact, any two orthogonal states, or in general, any collection of orthogonal states will be perfectly distinguishable, because you can perform some unitary transformation and then make a measurement, and those states will then be distinguished by that measurement. Okay, okay, let's make it a little more complicated. Say I've got a state, it's either a 0 or 1, and now I'm going to flip a coin to decide whether to perform an H or not. So I secretly flip a coin. So now I started with a 0 or 1. I flip the coin. I either perform an H or I don't. And now I hand you the state. So at that point, the state is either a 0 or 1 if I didn't perform an H, or it's a plus or a minus if I did perform an H. So what do? Well, maybe you don't know what my coin flip was, but you have a coin of your own. You can flip your coin and then decide to do an H or not do an H. Okay, so let's suppose that our coins agree. If our coins agree, then you're going to be able to tell whether I had a 0 or 1 initially. And if our coins disagree, then you're not going to get any information out of that. Does that make sense? So if I've performed an H, getting a plus or minus, and you don't perform an H, then you kind of get something random. But if I performed an H and you perform an H, then we're back to the original state, and you can figure out whether I had a 0 or 1. And suddenly, in that case, 50% of the time, now we're sharing a bit of key. So
how can we tell whether or not we're sharing a bit of key?
Well, so what happens is then, excellent question. So how can we tell? Well, we then reveal what basis the results of our coin flip. And after we've revealed the results of our coin flip, then we know. And if we do this 100 times, we're going to share 50 bits of key. Now, suppose you're trying to eavesdrop on this. Well, you've kind of got a problem. Here's your problem. The problem is that when you see these quantum bits flying back and forth, you kind of want to know what they say. So you're going to have to make a measurement on those qubits. And the minute you make a measurement, then it's going to change the state. And so you and I are going to be able to detect that. It turns out if we sacrifice a few bits of our key, so we do this 100 times, now we share 50 bits of key, and then in order to make sure there was no eavesdropper, maybe we pick 10 of those bits that we know are in common. Now we share those publicly, kind of destroying their keyness. But and if there's any errors in those bits, then we know that somebody's sort of eavesdropped. And then there's a theorem associated to this, and the theorem is that this is sort of unconditionally secure cryptography. It's called BB84, and the precise statement is something like, in order for an eavesdropper to get a meaningful amount of information in the key, that the eavesdropper reveals their presence with probability that exponentially approaches 1. So that's kind of the...
eavesdropper can make sure you never get a service attack.
Yeah.
Sitting there and looking at stuff, it will make sure that you never get to do anything.
Right. Okay. Yeah. So I'm not an expert in any of this crypto stuff, but I just kind of wanted to give you guys. I mean, some of you guys are, I guess, and I kind of wanted to give you an idea that even with this very simple setup, we're kind of doing cryptography that has.
Just like setting that apart. So how do you? I didn't quite get. Like, so you're exchanging these keys.
Yeah.
And the guy in the middle may have observed them or not. So how do you know if they did that? Because if they observe them, things will collapse and you'll always get the same answer. How do you know if it was your observation or their observation that caused that?
Oh, because you've done this 100 times, and then you reveal what bases you use for each of those 100 times, and there's likely to be about 50 times when you actually use the same basis. And in the event that you use the same basis, what we saw before is that you actually, 100% of the time, you get the right result. So if there's no eavesdropping, then all 50 of those bits should be uncorrupted. They should be identical. You and I should share 50 bits of purely equal key. So what we do is we pick maybe 25 of them, and then we sort of authenticate those by sharing them. And if any of those are off, then we...
Right, so it seems like each time an eavesdropper looks at a bit in transit, there's sort of a 50% chance that it'll be evident that was eavesdropping has happened.
Yeah, I mean, if you think about it, like if the eavesdropper picks the wrong basis, then the eavesdropper is going to collapse it to a state that's a 45-degree angle away from what it was, and then it's going to get sent on to Bob, and Bob is going to, there's going to be a good chance that Bob gets the wrong answer when Bob does what he's doing. Yeah, and it's more subtle than that. Of course, the eavesdropper could do something like a 20-degree rotation. But part of the theorem is that doesn't actually help the eavesdropper. The eavesdropper can do a whole bunch of things, but in order to actually extract information out of the key, the eavesdropper reveals their presence. Yeah. Question?
Yeah, so for these transforms, like the Hadamard, are there physical representations of these? Like in a quantum computer, can they do that transform?
They better, if they're claiming to have a quantum computer. I mean, I think it's fair to say that human beings at the moment are very poor at representing 50 qubit states, but they're very good at representing single qubit states and transporting them over distances of hundreds of kilometers. We can do that. I think there's even reports of doing it up to satellites and that kind of thing. So yeah, I think this is sort of, this crypto stuff isn't what I do, but I kind of wanted to mention it because I thought you guys might be interested in it. And I think if there's any sort of quantum stuff that's going to be applied in the near future, I think this is something that is definitely high on the list of things that are doable quantumly. Okay, so anyway, that's a little bit about. Okay, so what I want to talk next about is something called Deutsch's algorithm. Um, okay, so here's a very simple game. I'm thinking of 2 bits, so B0 and B1. And I want you to tell me what the mod 2 sum of those 2 bits is, the exclusive OR of those 2 bits. So what is B0 plus B1? And you're allowed to make queries of me, and the queries have the form, what is the ith bit? So a query inputs I and outputs B sub I. And the question is, sounds almost like a silly question. Every time I say this out loud, I think, why am I saying this out loud? But the question is, how many queries do you have to make in order to determine the mod 2 sum of the bits? Well, if you have a single query, then obviously you get no information about what the mod 2 sum is. So what we say is that the classical query complexity of this problem is 2. So the query complexity is the number of queries necessary to determine this desired information.
What does that mean, the number of queries in the worst case? It's like with and, maybe, knowing 1 bit is enough.
Yeah, so you could say what's the smallest number that you need to determine with certainty what the outcome is, or you could say with high probability. Let's just say with certainty for the moment. So what I'd like to show you is that, and this is actually historically one of the very first advantages of classical, of quantum computing over classical. I'd like to show you that there's a corresponding, you could call this a concept learning problem. So in general, what you have is a student and a teacher, and the student is allowed to make queries of a certain form, and the student's trying to learn something. So for every such classical learning problem, there's a corresponding quantum learning problem. So I'm going to try to show you how that works, and hopefully show you that we can do better quantumly than classically. So here's the corresponding quantum learning problem. So if you think about how to do this classically, probably what you're going to do in your computer's memory is you're going to have 2 registers, one that stores the query and one that stores the response. And what's going to happen is, you have some query here and some nonsense in the response register. And then when the teacher goes and sees the query, the teacher overwrites B with B sub I. I shouldn't have called it B. B is, I just call it some nonsense, X. Overwrites X with B sub I. This is not a reversible operation. We sort of violated something. We the first thing to do is sort of make this reversible classically. So there's a very easy way to do that, which is instead of overwriting whatever is in the response register, what we're simply going to do is add in the desired bit, like that. So we're going to do IB or IX goes to ix plus bi. Okay, so you might call this a reversible version of the classical oracle. So this is reversible classical oracle. Okay, well, the quantum version of this is simply to linearize it. So what does that mean? It means that instead of putting in a pair of bits and mapping those bits to this pair of bits, you're going to allow putting in a superposition of these pairs of bits and map them to the corresponding superposition of these bits. So here's how the quantum oracle works. Quantum oracle works as follows. So it's going to be, we're going to call this O sub b. This function depends on b. It's going to be a function that takes in a pair of qubits, C2, tensor C2, and returns a pair of qubits, C2, tensor C2. To tell you what a linear map is, all I have to do is tell you what happens to a basis of this space. Well, the basis of this space consists of pairs of bits. So I'm going to tell you exactly what it does. It sends I, comma x to I, comma x plus b sub I. So as an example, let's suppose that the hidden bits were 0 and 1. So suppose b is equal to 0, 1. And let's see what O sub 0, 1 does. So O sub 0, 1 will, well, there's 4 possibilities for what the inputs are here.
There are 4 possibilities. These are kind of after measurement.
There's no measuring yet. We're just, so we've created a 2-qubit state where this is the query register and this is the response register.
I mean, why is plus not an option? What is it called? Plus. Is that a number?
Yes. Plus is a linear combination of 0 and 1. So if you know what happens to 0 and 1 under a linear map, you know what happens to plus. Yeah. In fact, in a second, we're going to be doing exactly that. Because let's just follow through this example. So you can think of how does this oracle work? The teacher looks up what the value of b sub I is and then adds it into the second register. So let's just, just to kind of make this very concrete, let's compute what these are. So 0, 0, 0 is the query. The teacher looks up what's in the bit 0, that's a 0, and adds it into the second register. So that's 0, 0. Again, teacher looks up bit 0, 0, adds it into there, so that's 0. What happens to 1, 0? Well, the teacher looks up what's in bit 1. What's in bit 1 is 1, adds it into there. So this goes to 1, 1. Here the teacher looks up bit 1, it's a 1, adds it into there, and gets 1, 0. Okay. So what we have here is a linear transformation from a 4-dimensional space to itself, and it takes the 4 basis vectors and permutes them in this manner. If you wanted to write this as a 4x4 matrix, it would be very easy. It would be this matrix like that. It's a 4x4 permutation matrix where the first two basis vectors go to themselves and then the next 2 basis vectors get switched. So this is a unitary function from C2 cross C2 to itself. Okay. So that's the quantum oracle. And then the question is, what's the quantum query complexity? So how many calls do you need to this oracle in order to solve this question of what the sum of the bits is. There's something common in this subject called the phase kickback trick. Explain to you how that goes. Let's follow through on your suggestion of putting plus in the response register and see what happens to I comma plus. So I comma plus is 1 over root 2 times I comma 0 plus I comma 1. So what happens? Well, when you apply the oracle, the teacher looks up what b sub I is and adds it into this register. Let's imagine that b sub I is 0. If b sub I is 0, this thing goes to itself, and this thing goes to itself. So this thing goes to itself if b sub I is 0. What if b sub I is 1? If b sub I is 1, that gets added into this state. So this state goes to this state. And this state will go to this state. They'll switch. Because, as they say, addition is commutative, this thing will go to itself regardless of what the value of. So this thing goes to itself. It goes to I comma plus, independent of the value of b sub I. Okay, well, that's bad news because we didn't pick up any information about b sub I from this. A much better thing is to put minus in the response register. If you do that, then you get the minus state is I0 minus I1. And then what happens? Well, if b sub I is equal to 0, then these guys stay put. So this goes to I0, or I minus, sorry, goes to itself, which is I minus. And if b sub I is 1, what happens then? Well, then these guys switch places, but when these guys switch places, you pick up a minus sign. So this goes to minus I minus. So what you essentially get here is you get minus 1 to the b sub I times I minus. So what you learn from this calculation is that I minus is an eigenstate of this transformation, and the eigenvalue in its phase encodes the ith bit of this transformation. And this trick is present in almost all of the quantum algorithms that exist. And maybe you can see why it's called the phase kickback trick, because you're sort of kicking back that phase. Okay, so here's the Deutsch's algorithm. We're going to create the state which is called which has plus in the query register and minus in the response register. And we're going to see what happens to that state. So we're going to send it to the oracle. Well, before we do, let's just write it out. It's 1 over root 2, 0 minus plus 1 minus. And now we're going to send it to the oracle. This state picks up a phase of minus 1 to the b0. So this is 1 over root 2 minus 1 to the B0 times 0 minus. And this guy picks up a phase of -1 to the B1.
So in the classical learning problem, we couldn't really ask queries that were complex numbers. So how do we sort of, what's the intuition behind why this is actually a reasonable representation of the classical problem when the kinds of queries we can ask are very different?
Well, that's a great question. So I guess the usual, let me give you the usual answer to that, which is that if you have, well, people talk about like a quantum database. So what's a database? It's something where you can look up any entry in that thing and see what it is. So what's sort of a quantum analog of that? Well, a quantum analog would permit you to sort of make a superposition of queries to that database, which is a linear combination of queries, and give you the corresponding linear combination of those answers. So I think, in my mind, it's a mathematical construct. I know that, and I've just told you exactly for any concept learning problem what the corresponding quantum concept learning problem is. So your question as to whether or not that's sort of a reasonable thing to consider, I guess, kind of depends on your point of view, I guess, right? Yeah. As a mathematician, I don't feel like I need to, I mean, I kind of see these things as being kind of interesting abstract mathematical questions. But, you know, I guess we're running short on time, but just to say, like, I think it's fair to say that there are some interesting quantum algorithms, like Shor's algorithm for factoring integers, which is maybe one of the reasons why in the 90s people got all excited about quantum computing, because a quantum computer can factor integers in polynomial time. I think it's fair to say that parts of that algorithm kind of resemble having a concept learning problem embedded in them. So you kind of imagine a lot of algorithms have a little subroutine where you have to compute something, and if instead of being able to compute that thing quickly, you're able to calculate a linear combination of that thing quickly, which is what quantum computing allows you to do, then having that quantum subroutine allows you to quickly solve the problem. So, so I think I don't know if that really answers your question at all, but yeah, okay, yeah.
Should that last line have a cat 1 minus?
Yeah, thanks. Which brings us back to the, see if we can follow this through. Yeah, so then we're going to factor out a -1 to the, I'm going to factor out a -1 to the B0, let's say. If you factor out a -1 to the B0, you're going to get maybe 1 over root 2. Let's maybe put that up here. Or just, yeah, 1 over root 2. 0 minus plus -1 to the B1 plus B0 1 minus. Okay, and then look at what you have in the first register. So in the first register is -1 to the B0. If this mod 2 sum is 0, then this is 1, so you get a 0 plus 1, you get a plus state. If B1 plus B0 is equal to 0, mod 2. And if B1 plus B0 is -1, or is 1 mod 2, then this gives you the minus state. If b1 plus b0 is 1. And now, now you simply make a measurement of the first register. First you perform a Hadamard transformation on the first register, and then you make a measurement. So then you're going to perform an H and then measure. And what you're going to get when you perform that measurement is 0 or 1 with probability 1. And you get B0 plus B1. Okay. All right. So as I say, you know, I mean, this is like the dumbest game on earth. You know, as a mathematician, like I'm like very partial to the idea that when you play really dumb games and you understand them really well, like things kind of open up for you. Like the cryptography that we were just talking about. It's really pretty simple with the rotating by 45 degrees, but it actually has applications. Yeah.
So I must have just missed a step here. When you tried factoring that out, well, in the first clause, you're multiplying through into what's in the bracket. So you got -1 to the b0 over root 2 times the first qubit.
Yeah.
Where does the 1 over root 2, how does that disappear? Is it because it's
that's in the
changed state to the
plus.
plus?
Plus
Okay.
is by definition 1 over root 2 times,
Okay.
yeah, the
Let's
sum
pick on
of this.
the
Yeah,
plus.
that's right.
Yeah, I got it.
Yeah. Other questions? Okay, so I think, am I supposed to go till 1 or am I supposed to stop at 1250 or? 1 is fine. Okay, so let me just summarize. I probably won't get to tell you many details of the types of things I'm thinking about personally, but that's okay. Let me just summarize. Next section is called Beyond Deutsch, because maybe you have tasks in mind that are more complicated than adding 2 bits. Anyway, I hope here we're convinced that T sub quantum is equal to 1, single query. We only applied the oracle once. So I'm going to call this Beyond Grover. Or sorry, beyond Deutsch. Grover is one of the things that's beyond. Ahead of myself. Okay, so there's something called Grover's algorithm, which is the game that's called Guess My Number. So I'm thinking of a number A. It's between 0 and n minus 1. What's my number? And you're allowed to ask me queries like, is your number 12? And I will respond with a yes or no. So that if you input a query I, I'll respond with 0 if I is not x, and I'll respond with 1 if I equals x. Okay, well that's a concept learning problem. What's the classical query complexity? No, I'm not doing a higher lower kind of thing on you. Basically it's n, but we might want to say n minus 1 because by the time you've guessed all the numbers that are wrong, you know that the remaining number is right. So the remarkable thing here is that the quantum query complexity is root n. And that's something called Grover's algorithm. So you get a quadratic speedup and it has a beautiful geometry. You know, if you're interested in this, maybe you've already seen it, or maybe you should look it up.
Is root n what probability? Probability 1 as before? Or
Yeah, mostly it's like with probability that's sort of arbitrarily close to 1, but there's actually an exact version of it that nobody knows about, but everybody knows it exists, where you do some weird thing at the end to get actually probability 1.
Is it root n quantum queries or n minus minus 1 classical queries. So it's a speed up if these have the same cost, right?
If they have the same
Cost.
cost, yeah, that's right. Right. There's something called the Bernstein-Vazirani algorithm. So it's a little more contrived. In that case, we have a mystery string, bit string of length n, and the queries are also bit strings of length n, so let's call it x in 0, 1 to the n. And what I tell you is the mod 2 dot product, a dot x mod 2. So classically, you can pick off the bits one at a time, so there's little n queries are necessary. T classical is equal to n, little n. And T quantum is equal to 1. So I don't know if you call that an exponential speed up or a super exponential speed up, but it's the best you could do. So, the problem's a little bit more contrived, but I mean, this is something you actually want to do, find items in lists. I'm not sure exactly why you would have access to an oracle of this type, but in any event, the quantum world is pretty good for this one. And there's a couple other ones that are of interest, just to mention. There's guess my period. So maybe you have some function that's periodic, like that. And everything's sort of discrete here, maybe. So this is like 0 to n minus 1. And I'm guaranteeing you that the function's periodic, and I want you to tell me what the period of the function is. And classically, this is very hard to do. You'd have to sample many values of the function before you can find the period. But it turns out that quantum period finding is very fast. It's sort of a polynomial in the log of n, and directly leads to Shor's factoring algorithm. Period finding, yeah. But again, it's a concept learning problem where you're given a function, you're allowed to evaluate the function, and you're trying to find some particular information about the function.
And how is period finding related to factoring?
Because if you want to factor, I think you took number theory at some point.
Just a long time ago.
That was a really memorable class. You guys were fantastic. So if you want to factor a number n, it turns out that that's computationally equivalent to finding the multiplicative order mod n of any integer a. And so that's kind of an exercise. But the multiplicative order of a number is the period of the function, I goes to a to the I. Yeah. So I can talk through more details of why this is equivalent to factoring with you later if you're interested in that. But it's kind of and then let me just mention one more problem that's partially solved and is of great interest to everybody, which is called the hidden subgroup problem, which is also in the same framework of hidden subgroup problem. Or HSP. So we've got some group G, and G is known to everybody, the teacher and the student. The teacher has a subgroup of G that's hidden, and the student has access to that subgroup in kind of a bizarre way, which there's a function from G to some other set X, which is guaranteed to be constant on the cosets of H. So constant on cosets of H. So in other words, all of H is going to the same element, and then a coset AH is also going to the same element.
But those two could be different.
They have to be different. Yeah. Oh, sorry, and distinct. Yeah. Right. And so it's again, it's a very hard problem classically. Even to get any information, you sort of have to hope that you get a collision of values, and that's not going to happen randomly, depending on the size of the subgroup. But here's the facts. So this is for abelian groups. If G is abelian, this is equivalent to Shor's algorithm. It's equivalent to the quantum Fourier transform or the period finding, and is solved.
The question to find H.
Yeah, find H. Sorry. Yeah. Problem. Find H. The very first non-abelian group that you look at in group theory class, which I'm teaching right now, is the dihedral group, D2N, and nobody knows if there's a polynomial algorithm for doing this on a quantum computer. And people are greatly interested because if you can solve this problem, you can solve the shortest vector problem in lattices. So if, among other problems that you might want to, I don't know if people care about lattices around here, but getting some laughter there. So I'll take that as a yes. And then for symmetric group, so permutations, it turns out that for permutations, it turns out we also don't know whether this can be solved. And but if we can solve it, then we can end up solving the graph isomorphism problem. So obviously there's a lot of interest in that. And then just to sort of, in the remaining 30 seconds, just to give kind of a plug to my own research and my research with my former student Daniel Copeland, who's now at UCSD. You can find our paper on the archive. But basically the problem that we analyzed was suppose that your oracle, so you have a group G, and your oracle is a representation of G. So O sub G, so G maps to O sub G is a representation of G. So in that sense, these oracles are the most symmetric they could possibly be. The oracles themselves form a group. And in that case, it turns out, as we discovered, that the representation theory, if you understand the way that irreducible representations tensor together and decompose into irreducibles, you can actually completely analyze any quantum learning problem that has this much symmetry. It turns out the hidden subgroup doesn't have quite that much symmetry, so we sort of unsurprisingly we haven't cracked this mega open problem, but hopefully this setup kind of sheds some light maybe on some of these things that are a little bit less symmetric. So I'll stop there.
Are there any questions? That's the few me.